We've been looking in 2.7. Did anybody have any homework questions there? 2.7.
And we talked about the landscape 8-1, as it was worded weird. That was only 7-1.
Landscape 8?
Yeah.
So that one is the one that had numbers that were bigger than this number and smaller than this number. So this number has a 2 in its 1, 2, 3, 4, 5, 6, 7th decimal place, and this one has a 3 there. So we need to be bigger than this number with the 2 in the 7th decimal place by having a 2 in the decimal place. That's the 7th position, and all these numbers do. And then the ones that have digits after the 2 that aren't 0, make them bigger than this number with the 2 in the 7th decimal place, but still smaller than this one that would have gone to a 3. But there you had to find the ones that were rational. So to be rational, you would end in a repeating pattern. So this one did with 3s, with 0s, or with 0s. Okay. Any other questions? We started this section in 2.7 by asking if there was a number between 0.9999 and the number 1. And I'd asked you to write down what you thought about that, if there is a number in between there or not. So hopefully you wrote that down and you can decide now. So we spent quite a bit of time looking at the numbers. We found that between any two rational numbers, there's another number, another rational number, and another irrational number. And between any two irrational numbers, there's another rational number and another irrational number. So, how about between these two numbers? Can we fit a number in between there?
Yep.
Okay, what number?
0.9999.
So these little dots mean that these 9s go on forever. Yeah, so that's what those little dots mean. Okay. Okay. Anybody else have any ideas? Because that was the approach we took, right? We just put one more decimal place and then we squeezed one in. But here, these 9s go on forever. Does that mean 0.9999 ... is next to the number 1? Is that the number that's next to number 1? What number is next to 1?
It'd be 0 or 2.
So 0 and 2, those are the integers that come before and after. But there are some numbers in between those, aren't there? So for example, what would be a number closer to 1 than the number 2 is? 1.1. Is there any number closer to 1 than 1.1?
1.000001.
Okay, so that's closer. That's closer to 1 than 1.1 is. Is there a number closer to 1 than this number?
Add numbers
add another 0. So every time we get close to 1, we can always get closer yet. But this has the notation with the dot, dot, dot at the end. I mean, we don't have that notation on the right side with the zeros, numbers to the right of 1. But we do have that notation getting close on the left side. Well, let's use the work that we did in section 2.7 to write this as a rational, to write this rational number as a fraction. So we learned how to take numbers that end in a repeating pattern and write them as a fraction. So we'll go ahead and do that with 0.99999. Okay, that will be our n. So these 99999s, these go on forever. Just keeps repeating. And that's the n. What power of 10 do I multiply by here? 10. 10, yeah. So there's one digit repeating, the number 9, so we multiply by 10. So that will move my decimal 1 to the right, so I'll have 9.99999. And those 9s go on forever. And then we subtract the n. So we're subtracting the 0.999, so we line up our decimal places. Ten n minus 1n, that's 9n. And here when I subtract, those 9s are lining up, so they subtract away. I'm left with 9 minus 0, which is 9. So I have 9 times n equals 9. I'll divide both sides of the equation by 9. N is 1. That's our number. So the rational number 0.999 repeating is equivalent to 1. They're the same number. So this particular number has two different names. The name 1 and the name 0.9 repeating. They're equivalent. They're the same number. Just written differently. So when we ask, is 0.9999 next to 1, the answer is no. There is no number next to 1. The numbers aren't like that. You can always squeeze another one in. The reason we couldn't squeeze one in here, in this case, is because they were the same number, just with different names. So that's kind of weird. You don't usually think of 0.9 repeating as equivalent to 1, but they are in fact equivalent. Does anybody have any questions? Okay.
I just want to make sure. So the reason that it's 10 is because there's only one repeating number versus like if it was 9292, that would be times 100 then.
Exactly.
Okay.
So if we'd have been looking at 0.9292 repeating, we'd have taken a 100 times n.
Okay.
Yeah. Any other questions? That brings us to chapter 3, where we're looking at infinity. So in 3.1, we begin to look at infinity. Your author begins section 3.1 with the question, what comes to mind when you hear the word infinity? write your thoughts or questions on a piece of paper. So I'd like you to take a minute to do that, please, and then I'm going to ask a couple of you to share. So online students, you should go ahead and write those questions down also, or ideas. Do we have any philosophers in here? Because that's kind of a question in itself. Is infinity an idea that belongs to the realm of philosophy, or maybe religion or literature? Why would it fall into mathematics? Well, how about you tell me what some of your thoughts were that came to mind when I asked you to write about infinity. Would anybody mind sharing, please?
Just going on forever. Endless.
Going on forever? That makes sense. Did anything in particular going on forever come to mind?
Numbers.
Numbers going on forever? Sure. What about you?
I thought of space.
Space? Does space go on forever? I wonder.
It does. It always expands.
It always expands? What other ideas came to mind?
Never ending.
Never ending? Did anybody have questions that came to mind? Well, some of these ideas we're going to look at. One of the, your author says that one of the great successes of the human intellect is to take this vast idea of infinity and to tame it, to make it susceptible to reason. Before we tackle such a big subject, we first look at finite. Now, mathematicians like to do things with quantifying, right? Numbers. So when we say finite here, we're going to look at finite sets. So sets are just collections of objects. We usually call those objects elements. We could look for collections of finite sets right in this classroom, for example. We could say the set of these little braces, these kind of curvy ones with a little point in the middle, these are called braces, and they're read the set of. So, the set of markers in the classroom. That would be an example of a finite set in our classroom. Can you give me some examples of other finite sets, either in the classroom or not in the classroom?
Male versus female.
In the classroom?
Yeah.
So you said the set of men in the classroom, or males you said?
Yeah.
Males in the classroom. And you said the set of females in the classroom?
Yeah.
Those are both finite sets. Any other examples?
Chairs.
Chairs in the classroom? There you go. So I think you have a good idea for what finite sets are. We're going to do a lot of comparing of sets. So comparing sizes of sets. Let's talk about that a bit. Now let's look at two sets in the classroom and see if we can compare the sizes of those. Okay, so we'll look at shoes in the classroom. And we'll look at feet in the classroom. So I want to compare the size. I want to know which one's bigger. Well, one way to do that is just to ask you all, is anyone barefoot? It's kind of warm out today. Anybody barefoot? Okay, nobody's barefoot. Does anybody have a set of extra shoes with them? Anybody going to the gym maybe? Have a set of extra shoes? Have another pair in case your feet start hurting? Anybody have extra? You have extra set of shoes? Okay. So everybody has shoes on, and there's at least one set of extra shoes in the classroom. So which set is bigger? Shoes or feet? Shoes, yeah.
Assuming everyone has 2 feet.
That's true. Well, even if you don't have 2 feet, you probably wouldn't need 2 shoes then.
You can ask if they don't have more than 2 feet though.
Yeah, good question. Does anybody have more than 2 feet? I think I kind of would have noticed. I'm pretty observant, but that I might have noticed. That's true, yeah. Okay, so you could qualify that a bit. How about if we look at the number of people in the classroom and the number of cell phones in the classroom? So look at the two sets. Look at the number of people in the classroom and the number of cell phones in the classroom. So I did not bring my cell phone. I don't bring my cell phone to class unless there's some kind of emergency going on. Did anybody else not bring their cell phone? Okay. Who has an extra cell phone? Sometimes people have extra cell phones. Any extra cell phones? Okay, nobody has an extra cell phone, and I didn't bring a cell phone. So which set is bigger here? People. Yeah, this one's bigger. Okay, how about if we take people in the class and computers? Because I do have a computer if you count the one up here. So not cell phones this time, but either a tablet or a PC, not cell phones. Okay, so who does not have a computer or a tablet? Okay, so 4 people don't. Does anybody have an extra? Like you carry 2 tablets or 2 PCs. Have any extras? Okay. So this time the people in the classroom were bigger as well, a bigger set. What we've been doing is a 1-to-1 pairing. We've been matching up, just like your fingers matching up, set of fingers on one hand, set of fingers on the other, and match up 1-to-1. And that's how we've been telling our set sizes. We're looking to match up the elements. We're checking to see is there no extras and every element matched. So nothing gets left out and there's no extras. That's how we've been telling if these are the same size sets. That's a 1-to-1 pairing when you can do that. Or sometimes we'll call that a 1-to-1 correspondence. When you can match one element to one. So if we didn't have any that were the same size. Maybe we'll see some that are the same size in a little bit here. But if we can have every person in the class have a computer, that would have been a 1-to-1 if there were no extra computers. Okay. If I had brought my cell phone, we would have had a 1-to-1 pairing with cell phones and people in the classroom. So let me put some examples down and you decide if there is a 1-to-1 correspondence between these sets. These would all be good quiz questions. Is there a 1-to-1 pairing between? And then I'll give a couple of different examples. Is there a 1-to-1 pairing between A, students in the classroom? Now don't tell the answers because I'm going to ask you to write these down. Students in the classroom, noses in the classroom. Okay, so don't tell the answer. You're going to write down the answer. B, people in the classroom. People in the classroom and faces in the classroom. People in the classroom and faces in the classroom. C, feet in the classroom. Feet in the classroom and people in the classroom. Now don't tell the answers, write them down.
I have a question.
Okay, what's your
When
question?
you say faces, do you mean like human faces or like can you count the face of the clock?
Oh, that was good thinking. So the question was, do we count the face of the clock or do you mean human faces? So I meant human faces. If you have a question on a quiz and you have to qualify it like that, you can go ahead and write in your qualifying idea, okay? Or just take it that I'm not trying to trick you. Okay. All right, so what did you write for A? Is there a 1-to-1 pairing between students in the classroom and noses in the classroom?
No.
Oh, that was a trick one. It was no. Why was it no?
Because you're the teacher.
Because I'm the teacher and the teacher has a nose. Okay, how about, is there a 1-to-1 pairing between people in the classroom and human faces in the classroom?
Yes.
Yes. And C, feet in the classroom and people in the classroom? No. This is 2 feet for one person most of the time. So 1-to-1 pairing, 1-to-1 correspondence. We're trying to line up exactly 1-to-1. And I keep putting my hands out like this, and I'll do it throughout this chapter because I want you to remember 1-to-1 pairing, you line up every single one, okay? Every single one in one set with every single one in the other. No extras, none are used twice. Let's make some 1-to-1 pairings. Let's make a 1-to-1 pairing if possible. So we'll make a set called A. Sets are often named because then you can talk about them. So we'll make a set called A, and it will have the numbers 1, 2, 3, 4, 5. Then we'll make the set called B, and it will have the letters A, B, C, D, E. So to make a one-to-one pairing, we would indicate that with a double-headed arrow. So we would say the one goes with the A, okay, and that's like lining up your fingers, the one pinky with the pinky, and so on. We're just lining them up, and I'm using arrows to do that. So 1 with the A, 2 with the B, 3 with the C, 4 with the D, and 5 with the E. These would be good quiz questions also. Make another set. How about we make a set with the numbers 1, 2, 3, 4, 5, and the set of numbers 2, 4, 6, 8, 10. Could you make a one-to-one pairing there? Yeah. So, and again, you don't have to put the 1 with the 2 and the 2 with the 4. I just can write shorter arrows if I do that. I mean, if you wanted to, you could put the 1 with the 10 and the 2 with the 5 and so on like that.
How would
You just draw longer arrows then. Okay.
why
So,
would you match them up?
so if you wanted, you could put the 1 with the 10 over here, and the 5 with the 2 over here, and the 2 with the 8. It's just so you have 1 of each of the first set going with 1 of each of the second set. So what we've been looking at is how to tell if two sets are the same size by lining them up 1 to 1. So let's write down what we've been doing. Two sets are exactly the same size. Two sets are exactly the same size if and only if two sets are exactly the same size if and only if their elements can be put into a 1-to-1 pairing. Two sets are exactly the same size if and only if their elements can be put into a 1-to-1 pairing, or we could write correspondence there. So what mathematicians and philosophers mean when they say if and only if, they mean this sentence goes both directions. Two sets are the same size if their elements can be put into a 1-to-1 pairing, and the other way as well. If the elements can be put into a 1-to-1 pairing, then the two sets are the same size. Okay, everybody stand up, everybody up, stand up. Okay. Now, raise your right hand, cross your heart, swear. We're going to read this together. Everybody read this out loud together. Two sets are exactly the same size if and only if their elements can be put into a 1-to-1 pairing. Okay, thank you. You can sit down. So the reason we're all swearing to that is because it's easy with finite sets. However, when we get to infinite sets, it can become disturbing. In fact, it took several decades for the mathematical community to accept ideas about infinity in the chapters that we're going to be seeing. Now, this is your class activity for 3.1, so you could put your placard, your name placard there, or write your name next to it. Take a photo, or you can type it in. If it's easier to type than to take a photo, you feel free to type that in. You want everybody to understand putting into a 1-to-1 pairing, saying that making two sets be the same size if and only if they can be put into a 1-to-1 pairing. we are going to go on to 3.2 then. Does anybody have any questions before we go to 3.2? The author opens this section with the question, how much bigger is the set of rational numbers than the set of natural numbers? How many fractions are there between 0 and 1? So we've looked at the, an infinite amount of fractions between 0 and 1. And we've looked at how between every two rational numbers there's another rational number. So this is very curious. We will be spending more time on answering this question later on in section 3.2. First, we'll go back to looking at finite sets in preparation to being able to talk about infinite sets. These are my notes here. I will write them down. Okay, finite sets. So we're still talking about infinity in 3.2, but we work up to it and we talk more precisely about finite sets. Let's take a look at what is the smallest possible number of elements in a set? What is the smallest possible number of elements in a set? So we had some sets. What was the last set we looked at? Had the numbers 1, 2, 3, 4, and 5 in it. So you could have 5 elements in a set. Could you have a smaller set than that? Whoops. Went the wrong way. What would be the smallest possible number of elements you could have in a set? 1. In fact, the set could be the number 1. Could you have a smaller set than that? Is there such a thing as an empty set? Have you maybe talked about the empty set in math ever? Yep, the empty set. So you can actually have a set with no elements. Let's define a finite set. A non-empty set is finite if there is a natural number A non-empty set is finite if there is a natural number n such that there is a one-to-one pairing such that there is a one-to-one pairing between the set and the set one, two, three, comma, n. A non-empty set is finite if there is a natural number n such that there is a one-to-one pairing between the set and the set 1, 2, 3, comma, comma, n. let's look at an example. So I picked the days of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Is the days of the week a finite set? Yes, I see heads nodding, yes. And what is the number n that can let me make a one-to-one pairing? Yeah, 7, good. And we demonstrate that pairing with the little arrows. And again, I'm going to make my one-to-one pairing just Sunday goes with 1, Monday with 2, Tuesday with 3, Wednesday with 4, Thursday with 5, Friday with 6, Saturday with 7. Now, we're going to make sure that none are left out. Everybody's used up. All the elements are used up, none are left out, and none are used twice. So you don't have a one-to-one pairing otherwise. And that seems kind of simplistic with the numbers 1 through 7 and the days of the week. And it is simplistic, but we're headed toward infinity, so we want to have a solid grasp of the simple before we move to infinity. So that's an example of what we are talking about in our definition. You have to have a number you can count up to. And that number is the n right here for your set to be finite. Now, for your set to be infinite, what would that look like? A non-empty set. A non-empty set that is not finite is infinite. A non-empty set that is not finite is infinite. What would be some examples of some infinite sets? Who can think of some infinite sets? Sets that go on forever.
Stars.
I think the set of stars is finite at any instant. Like they're winking out and growing, but if you took an instant in time and we had all the time we needed to count, I think we could come to an ending number. But there's definitely a huge set.
Like the dots beyond?
Pardon?
Never mind. They, that's the.
I don't know if it's like infinite, but it's always changing. It could be like the number of like hairs on her body because some are like falling off, or like I don't know if that's infinite.
Yeah, I don't think the number, yeah, you're right. The number of hairs is a finite set and your body. What did you think of?
So you could just say numbers.
Numbers. Yeah. So what would be a set of numbers that's infinite?
All the numbers.
Yeah.
All the numbers?
Yep.
Mm-hmm. All the numbers. That's true. All the numbers. Good. And we had a lot of different sets of numbers too that you could pick out of that. In fact, your author talked about 2 in the question for today. It talked about the rational numbers and the natural numbers. So the rational numbers remember those that could be written as fractions? And then we had natural numbers in that as well. The natural numbers are easier to list. because remember those are the counting numbers, so they go 1, 2, 3, 4, dot, dot, dot. The rational numbers, you could write out their definition if you want. A divided by B, where B is not 0, and A and B are integers. That gave another set of numbers when we said that, the integers. Maybe that's why mathematicians laid claim to infinity, because we have all these nice sets to talk about that are infinite. Well, let's prove one of these sets is infinite. Let's prove the natural numbers are infinite. So the natural numbers, the numbers that we count with, 1, 2, 3, 4, dot, dot, dot. Prove the set of natural numbers is infinite. The proof for this is the same as what you do when any of your aunts and uncles, right? When your niece or nephew comes up to you and says, Auntie, I've just found the biggest number in the world. It's 5,699 gazillion. Okay, so we'll be like that kid. We'll assume there is a largest natural number, and we'll just call it n, not whatever I said before. Well, you being smarter than your nephew or niece, you would pat them on the head and say, I'm sorry, Junior. However, there is a bigger number. And what would you say the bigger number was?
N plus 1.
Yeah, you did n plus 1. Yeah, good. But n plus 1 is bigger. So just like when we were proving the square root of 3 was irrational and we first assumed it was rational and arrived at a contradiction, that's what we did here. If there was a largest natural number, then it would be a finite set. However, we have one that's bigger, a contradiction. So there is no largest natural number. So there is no largest natural number. The set of natural numbers is infinite. Our initial assumption was incorrect. Well, let me give you two sets to think about. Here's the natural numbers. Sometimes those are abbreviated with the n with a double bar like that. So the set 1, 2, 3, 4, comma, dot, 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 the natural numbers, which you can abbreviate with a capital N with a double bar. And I'll make another set we'll call A. A starts with 2. And then it goes on 2, 3, 4, 5, dot, dot, dot.
Is that one?
A is the set so it's a little brace, 2, 3, 4, 5, dot, dot, dot.
No, above that.
So that starts with 1.
Yeah, and it says equal to,
N with a double bar. Yeah.
what does the double bar mean?
So that's an abbreviation for the natural numbers. Whoops. So N with a double bar is an abbreviation for the word natural numbers, the set of natural numbers. Well, I have to ask you, which is bigger?
The first one.
N or 8? So the first one is bigger because I took the 1 out. Right? So the second set doesn't have a 1 in, is what you're saying. So that means it's bigger. Let's go back to our definition. Where did we stand? We stood up and swore with our hands in the air. Two sets are the exact same size, exactly the same size, if and only if their elements can be put into a one-to-one pairing or a one-to-one correspondence. So when you say that the first set's bigger, that means it's impossible to have a one-to-one pairing. Does anybody say it's impossible, or does anyone see a one-to-one pairing so that it's not impossible?
I don't think it matters that the one's gone because it keeps going.
You don't think it matters because the one's gone because it keeps going? Are you?
Yeah.
What would be a one-to-one pairing then? So that none are missed, none are used twice. So what would I give the one? What would the 1 go to?
2.
2. Okay. 2. 3. 3.
4.
4. 4. 5. How about 500? 500. What would 500 in N go to?
501.
501. Okay. Does that mean none are missed? Everyone is going with another? Yeah. None are missed because no matter what number you pick out down here, you know what number goes with up here. No matter what number you pick out up here, you know what it goes to down here. So none get missed. Did we use any twice? No, we didn't use any twice. Okay, so these are in fact the same size. We say they have the same cardinality. Cardinality is a word we use in particular when we're talking about two sets. So the same cardinality to the same size. But that is one of the odd things that happens when you're looking at infinity. You took away 1, and yet they're still the same size sets. They're still a one-to-one pairing. You can take each element in the first set and match it with each element in the second set. They're the same size. We're going to talk more about this because it is a strange topic. We'll talk more on Wednesday. I'll see you then.